You know, when you look up at the night sky, you see all the obvious stuff. Stars, planets, maybe a galaxy if you're lucky. But hiding in plain sight is one of the quietest, biggest puzzles in all of science. It's a question about the very recipe of our universe.
It sounds like a simple question, right? Why is the universe made of these specific things in these specific amounts? We've gotten pretty good at figuring out what the universe is made of, but the why? That's a whole other story. The thing is, the amounts don't seem random at all. In fact, they might be a huge clue, pointing to some kind of deep, hidden connection we haven't seen yet.
So get this chart really puts it into perspective. Everything we can see, every star, every planet, every galaxy, you, me, everything, all of that makes up only about 5% of the universe. Just a tiny slice. The rest is this other stuff, mysterious dark matter, and the even more baffling dark energy.
And this is where things get really weird. Physicists have a name for it, the cosmic coincidence. Now, dark matter and the visible matter we're made of are supposed to be completely different things, right? They don't interact, they play by different rules. And yet, there's only about 5 times more dark matter than visible matter. I mean, on a cosmic scale, a 5-to-1 ratio is practically nothing. It's like they're next-door neighbors, which strongly suggests they might share some kind of common origin story. So that's the puzzle, right? That's the big information gap that a recent theoretical paper is trying to fill. It puts forward a really ambitious model to explain this coincidence and a lot more. So for this explainer, we're going to ask that key question. What does the study actually demonstrate? And, just as important, where do its conclusions have to stop? Okay, so here's how we're going to walk through this. First, we'll dig into this tale of two matters. Then we'll look at the incredible ambition of this new theory. After that, we'll see how the researchers simulated the universe's first second and check out what they found. Then we'll hit the pause button and talk about the crucial limitations, before wrapping up with why this is still such a powerful unifying clue. All right, first up, let's really set the stage for this puzzle. In our cosmic story, we've basically got these two main characters, the visible matter that makes up everything we know, and the mysterious dark matter that seems to hold it all together. They live in the same universe, but their origins are two of the biggest unsolved mysteries in science. Okay, next section. And you gotta understand, the ambition of this theory is huge. The researchers here weren't just trying to solve one little mystery. They set out to see if one single, elegant idea could potentially tackle several of the most stubborn, long-standing problems in physics all at the same time. The stakes couldn't be higher. I mean, this paper isn't just aiming for one small win. It's taking a shot at 3 of the absolute biggest head-scratchers in all of physics. First, what in the world is dark matter? Second, why is our universe made of matter at all, instead of being annihilated by antimatter? And third, a really deep, thorny theoretical problem called the hierarchy problem. The goal here was to find one single key that could unlock all 3 doors. So what exactly is this hierarchy problem? Well, put simply, gravity is just weirdly weak compared to the other forces of nature. I mean, think about it. A tiny fridge magnet can beat the gravitational pull of the entire Earth. This weakness creates a gigantic, unexplained energy gap between the world of particles like the Higgs boson and the energy scale where gravity finally gets strong. And to physicists, that huge gap seems totally unnatural. So how do they propose to solve this? With a pretty wild idea called the Randall-Sundrum Model. Picture this. Our entire universe is like a thin sheet of paper. A brain, as they call it, floating inside a much larger 5-dimensional space. In this model, that extra dimension is warped, and that warping effect naturally explains why gravity feels so weak to us on our little sheet of paper. It just solves the hierarchy problem, no fuss. And this idea is the foundation for everything else they build. All right, so you've got this massive, ambitious idea. How on earth do you even begin to test it? It's not like you can pop over to the lab and create a baby universe. No, you have to go back in time, to the very first moments of the universe, using the only tool you have, mathematics. The secret sauce in their model is a mechanism called freeze-in. Now, older theories often imagine dark matter as a leftover from that hot, chaotic soup of particles right after the Big Bang. But freeze-in is different. It's way more subtle. It suggests dark matter barely interacts at all. Instead, it was produced really slowly, as regular particles in the hot soup would occasionally bump into each other and poof, create a dark matter particle that then just drifts away. So how does this actually happen?
How do our regular particles even talk to this dark sector to create dark matter? Well, the Randall-Sundrum model predicts two special particles that act like portals or mediators. One is called the radion, which is related to the size of that extra dimension. The other is a heavy version of the graviton. These two particles are the only bridge between our world and the hidden world of dark matter.
And I really want to be crystal clear about this. This was not a physical experiment. Their lab was pure mathematics. They used a complex set of equations to simulate how these particle populations would evolve in the insane conditions of the first fraction of a second of the universe. And that's the built-in limitation here, right? A simulation like this can show you a path that could work, but it can't tell you if that's the path the universe actually took. Okay, so they ran all these incredibly complex calculations. What did they find? Did they actually manage to cook up a universe that looks anything like ours? And the answer, amazingly, is yes. The model actually works. The calculations reveal that there is a viable parameter space. You can think of it like finding the perfect settings on a cosmic control panel, where this one single framework can simultaneously produce the right amount of dark matter and explain why we have more matter than antimatter. It just clicks. So let's break that down. As you can see in this table, the model hits all the right notes. It satisfies the observed dark matter abundance. Check. It generates the matter-antimatter imbalance through a neat process called leptogenesis. Check. And, crucially, its predictions don't conflict with any of our other solid cosmological data, like from Big Bang nucleosynthesis or the experimental limits from places like the Large Hadron Collider. Basically, it clears all the major hurdles you'd want a theory like this to clear. But, and this is a really important but, this is where we need to pump the brakes a little and be super clear about what this theory does not prove. First and foremost, remember, this is a model. It's a beautiful mathematical story, but it is not a direct observation. It does not prove that extra dimensions are real. It also has to make some reasonable assumptions about parts of the early universe we don't fully understand yet. So while the results are a fantastic solution within the model, they are not yet a discovery about our universe. Now, these aren't flaws in the study. This is just how good, honest theoretical physics works. It's about defining the boundaries of what we can say for sure. Okay, so with all those caveats, you might be thinking, so what? Why is this a big deal? Well, it's a big deal because even with those limitations, it gives us a massive, powerful, unifying clue. The true power of this paper isn't just that it might be right. It's the sheer elegance of it, the unification. Instead of needing three totally separate, cobbled-together explanations for dark matter, the matter-antimatter asymmetry, and the hierarchy problem, this framework shows how they could all just be different symptoms of the same underlying cause, a warped extra dimension. And here's the best part. This isn't just some beautiful idea that we can never test. It's actually falsifiable. The theory makes concrete predictions. It says there should be new particles, like those heavy gravitons, with specific properties. That means experiments like the Large Hadron Collider can actually go out and look for them. In fact, the reason we haven't found them yet already helps to narrow down where the sweet spot in the model might be. So let's circle all the way back to our original question. What can we responsibly say right now, based only on this paper? Well, I think the authors themselves say it best. This Randall-Sundrum framework offers a unified and coherent resolution to that cosmic coincidence problem, while at the same time consistently solving the hierarchy issue. It's a compelling blueprint for how the universe could work. And that just leaves us with this one kind of mind-bending thought to close on. This paper suggests that the answers to some of our biggest questions, what are we made of, why are we even here, might not be found in some new particle we can smash, but might instead be woven into the very geometry of space-time itself, hiding in a warped dimension just beyond our senses.